Myself Gautam Sharma. I welcome you all in a Sapience Education. So today I am going to discuss question number 10.16 from the thermal properties of the matter. So let us discuss this question. So before that we need to understand what they are asking. A child is running at a temperature of 101 degree Fahrenheit is given an antipyrine, that is a medicine that lowers the fever, which causes an increase in the rate of evaporation of a sweat from his body. If the fever is brought down to 98 degree Fahrenheit in 20 minutes, what is the average rate of an extra evaporation caused by the drug? Assume that the evaporation mechanism to be the only way by which heat is lost. The mass of the child is 30 kg and the specific heat of the human body is approximately same as that of the water. And the latent heat of evaporation of the water at the temperature is about 550 calorie per gram. Now let us see here. There is a child, he is suffering from fever and he has a temperature of 101 degree Fahrenheit. Now after medicine taken by him, its temperature become 98 degree Fahrenheit. Why so? Because there is a lots of evaporation happens, and whenever evaporation will happen, then it means that there will be uh, lower in temperature lower in the temperature will happen. Okay, so can we find that what is the temperature difference? So the temperature difference is 101 minus 98, so this is approximately equals to 30 degree Fahrenheit. So we should convert it into degree Celsius. So 3 degree into 1 by 1.8, so this will be degree Celsius only. So 3 by 1.8 degree Celsius. Okay, now we need to understand that how much he has lost. So Q lost is how much? Q lost, heat lost by the body is how much? So this will be mass of the body into specific heat of the body into delta T. So the mass of the body is 30 kg. Specific heat for the water we have to take, because body is full of water, so this is equal to 1000 calorie per kg degree Celsius. 1000 calorie per kg degree Celsius. So we can put here 1000 into temperature difference, that is equal to 3 by 1.8. So finally we have got this. So when we calculate this, so it will be approximately equal to 90 by 1.8 kilocalorie. Okay, so the 90 by divided by 90 divided by 1.8 is how much? So this will be approximately equal to, not approximately, it will be 50 kilo calorie. Now this heat lost is converted into excess water evaporation. Heat lost converted into excess water evaporation. Okay, so this is, it means that mass into latent heat of vaporization of the water is equal to 50 kilocalorie. And so there, from here we can find mass is equal to 50 kilocalorie means 1000 divided by latent rate of vaporization, that is equal to 580 calorie per gram. So when we divide it, so we will get 86.2 gram, and this evaporation take place, this 86.2 gram of evaporation takes place in 20 minutes. Okay, got it. So rate of extra evaporation is how much? Rate of extra evaporation and this is equal to delta m by delta t. So this is equal to mass is 86.2 divided by 20. So 20 minute. So it will be 4.31 gram per minute. If we convert it into seconds, so this is the rate of mass evaporation. This can be written in the form of a second. So this will be 4.31 divided by 60 gram per second. So this will be m dot, that is equal to 72 milligram per second. So I hope you have understood this. So I hope this is the perfect answer. Okay, now we should read this question first of all. A thermocol ice box is a cheap and an efficient method for sorting a small quantity of the in a sum in a particular. A cubical ice box of a size 30 centimeter has a thickness of this. If 4 kg of ice is put in the box, estimate the amount of ice remaining after 6 hours. The outside temperature is 45 and the coefficient of thermal conductivity for the thermal coil is 0.01 joule per second per meter Kelvin, and heat of the fusion of the water is taken like this. So let us draw the situation here. There is a thermocol box. You know that in summer it has been used to keep the object or any cold drinks or any fruits to be stored in the lower temperature. So before that we have to put here the ice. Okay, so the outside temperature is how much? 45 degrees Celsius, and inside temperature, since we have put here solid snow or ice, so it is approximately equal to 0 degrees Celsius. Okay, now there is a heat transfer. Okay, if you want to find the total area of the box, so total area of box is equal to 6a square. Okay, now heat current or heat transfer is, if heat will definitely go into this, so rate of heat transfer that is equal to temperature difference by L by Ka, where L is the length or thickness of the material. For example, there is a one side and its thickness is like this, so this thickness. Okay, so from here delta T is the temperature difference is 45 divided by length or thickness. The thickness they have given, thickness of the ice cube box is 5 centimeter or 0.05 meter into K, thermal conductivity. So the thermal conductivity of the coefficient of thermal conductivity K is given as 0.01 joule per second, and 2 area is how much? So area is 6a square, that is 6 into a, that is side is how much? 0.3 whole square. Okay, So this is the equation. We have got this equation, right? Now heat transfer rate into time is equal to amount of heat. So the amount of heat is equal to mass into latent heat of vaporization, sorry, fusion, because ice will melt. So whatever heat has been transferred, so that will be converted into the melting point of mass of melting. It will be get converted in the form of melting of the ice. So what will happen from here? We can write h dot into time t divided by latent heat of fusion. So h dot we have 40. If we have h dot, the value of h dot we have is 45 into 6 into 09 into 0.01 into the time they have given as a how much time, 6 hours. So 6 hour, so 6 should be converted into second divided by latent heat of fusion. So this is 335 into 10 to the power cube joule per kg. So all units are in standard. So when we put it and when we find, so the mass, amount of mass of the ice to is melted in a 6 hour is how much? 0.313 kg of the ice. Okay, so I hope you have understood this. So this is the amount of mass of the ice. Okay, I hope you have understood now. Now let us do question number 10.18. A brass boiler has base area of this and thickness is this, and the boiler water at it boils at a rate of 6 kg per minute when placed on a gas stove. Estimate the temperature of the part of the flame in contact with the boiler. Thermal conductivity of the brass is this, and the heat of vaporization of water is this. So there is a brass boiler like this. There is water inside it. Okay, and there is a heat which has been given from outside. Okay, and it is boiling. So since it is boiling water, so its temperature will be 100 degrees Celsius. So what is the temperature of the flame? So we want to find temperature of the flame. Okay, so here we know that the change in temperature will be temperature of flame minus 100 degrees Celsius. Okay, so this is the one of the equation. Now as per the question, it is telling that rate of mass of evaporation, that is dm by dt, is given as 6 kg per minute. It can also be told 6 by 60 kg per second. So this will be 0.1 kg per second. So this is the mass, the evaporation. Okay, so in 1 second what is the rate of heat transfer? So we can write here dq by dt, and this is equal to the heat transfer. See, whatever amount of heat has been given to this, it will get evaporated. So this means the amount of evaporation of the heat is ml. So here ml, that is the heat, divided by time t dt. So dm by dt into L into rate of vaporization V. So this dm by dt, so dq by dt is equal to dm by dt into LV. So dm by dt, that is mass of the evaporation is 0.1 kg per second into latent rate of vaporization. This is equal to 256 into 10 to the power cube, and this is equal to dq by dt. dq by dt is actually the heat transfer rate, and we know that the heat transfer rate h dot or h is equal to change in temperature by L by K. So from here we can find delta T as h into L by Ka, where L is the thickness. So L, the value of L given as 1 centimeter or 0.01 meter, and the area is given as 0.15 meter square. So here we need to put here the value of h, that is dq by dt, and it is only the h. So this will be 0.1 into 2256 into 10 to the power cube into L. L is the length, so this will be 0.01 divided by thermal conductivity of the brass, that is 109, and into area is 0.15. So when we will do this, so we will get 138 degrees Celsius, and this is equal to change in temperature. Now the change in temperature can be written as T final is equal to change in temperature plus 100. So change in temperature is 130 plus 100. So this will be 238 degrees Celsius. So the final temperature of 8 flame is equal to 238 degrees Celsius. So this is the required answer. I hope you have understood now. Question is explain why a body with a large refractivity is a poor emitter. So as we know that absorption plus our reflection and transmission, this is equal to 1. So the addition of the all this thing will be constant. Okay, a body with a large reflectivity, if this is your large, so alpha will be very less. So if there will be less alpha, it means that it will absorb less light, hence it will able to emit less. Or we can also say like this: a body with large reflectivity is poor emitter because good reflection or bad observer. Good reflector are bad absorber, and hence according to keep according to Kirchhoff's law, bad absorber are bad emitter. So I hope you have understood part 1. Now the part 2. A brass tumbler feels much colder than the wood tray on a chilly day. Very interesting question. Yeah, definitely. Wooden table or wooden chair will not feel such a cold as like brass. So generally, what happens? Good conductors take away body heat easily, and sudden loss of heat cause our body to feel cold. Our body to feel cold. But in case of wooden, it does not feel because wood is a while wood is poor conductor of heat of heat. So no loss, no absorption of of heat from our body, and hence we feel hot, less cold. Okay. Now question number C. An optical pyrometer for measuring high temperature calibrated for an ideal black body radiation gives a too low value for the temperature of a red hot iron piece in the open, but gives correct value for the temperature when same piece is in furnace. So let us show the current condition. Let us There is an iron body and it is at atmosphere, and there is another iron body but it is in furnace, and there is a optical pyrometer like this. There is an optical pyrometer like this. In its surrounding, what happens? It is a furnace, so everywhere temperature will be high. Temperature will remain constant. So whatever there will be an reflection, of the light due to red hot body. So what will happen? All the all the reflection of the body, will come at same intensity. But when we see the atmospheric case, so what happened? Let us consider one light from the iron came, but different light may come from the different side. For example, from the atmosphere, there may be the reflection from atmosphere, there may be the reflection from atmosphere. So atmosphere has low temperature, atmosphere has low temperature. So due to instability of temperature, it enables to record temperature properly. So I hope you all have understood now. Now let us do next D. In question number D, the earth without its atmosphere would be inhospitably cold. Means we can't live. So what actually happens? Let us consider there is a earth and there is a atmosphere. So atmosphere try to trap the heat whatever coming from sun. So earth's temperature is maintained at optimal so that living are possible. Okay. Now there is another question. It is E. Heating system based on circulation of steam are more efficient in warming a building than those are based on the circulation of hot water. This happens because steam has extra latent heat of energy. Steam has extra latent heat of energy, so it delivers more energy per unit mass, therefore it is more efficient. So I hope you have understood now. Now let us do next question. Next question, a body cools from 80 to 50 degrees Celsius in 5 minutes. Might calculate the time taken to cool from 60 to 30 degrees Celsius. The surrounding temperature is 20. See here, as per the Newton's law of cooling, as per Newton's law of cooling, we can directly tell that the change in temperature by time taken to cool is directly proportional to the delta T mean. So for example, case 1, if we draw the case 1, so this is 20 degrees Celsius and this is the 80 degrees Celsius and the lowest temperature is 50 degrees Celsius. So the change in temperature will be 80 minus 50, that is equal to 30. But when we talk about the delta mean, so before that we need to find T mean. So T mean is equal to how much? So T mean will be the average of 80 plus 50. So T mean is equal to 80 plus 50 by 2. 80 plus 50 by 2, so this will be equal to 65. So the t mean is how much? So t mean is how much? So this will be delta t mean is equal to 65 minus 20, so this will be 45. Okay, so this is the case 1. Now case 2 they have given the high temperature is 60, low temperature is 30, so the mean temperature will be, this will be 45 degree. Now the atmospheric temperature is 20, so the change in mean delta t is mean is how much? 45 minus 20, so this will be 25 degree Celsius. And if we talk about the delta t, so the delta t will be here 60 minus 30, that is 30. Now we need to use this equation, so we can also write this equation as delta t by time is equal to k into delta t into mean. So we need to create an equation. So when we create an equation, so what will happen? So if we create an equation, so we can have so delta t. So for case 1, this is case 1 and this is case 2. So for case 1, delta t is how much? Delta t is 30 divided by time taken is 5 minutes, and this is equal to k into delta t mean is how much? 45. This is equation 1. Now if we talk about the equation 2, so this will be delta t is 30 by time taken is t, this is equal to k into delta t mean is equal to 25 degrees Celsius. So this is equation 2. When we divide equation 1 by 2, so we will have t by 5 minutes is equal to 45 by 25. So from here we will have a time required for cooling is equal to 9 by 5 into 5, so this will be 5 minutes. So I hope you have got the desired result. So I hope the time taken to cool from 30 degree to 20 degree or 60 degree to 30 degree is 5 minutes. No, not 5 minutes, it is 9 minutes, sorry, 9 minutes. Okay, so I hope you have understood this section well. Thank you for watching my video. Hope I will complete next chapter. So